for problem size of small to the given instance size. It records the solution because of that it needs the space always. It maintains it, memorizes the solutions, whatever it is finding. But the same thing, the advantage is if the problem size is getting shrink, then also the answer is already available. Okay, and if it is getting extended with the known solution, it can be extended further. So that advantage is also there for because of the memorization, but it has the space complexity. But for some problems, uh, yeah, the time complexity will be still more. Okay, one such problem is this traveling salesman problem. Okay. Because the brute force approach is taking more time, we are actually coming for dynamic programming technique for optimization kind of problems. But even then, even when we are doing with the dynamic programming, the time complexity is more for some of the problems. Okay, one such problem is traveling salesman. How we are saying it is more? It's in the order of 2 power n or some maybe in the order of n factorial, that kind. Okay. But then will brute force be better than this? Not definitely. If you use brute force, that will be worse than this. Okay. So that's why we are going with dynamic programming. But if even dynamic programming is giving more time on that, then we have to go for approximation, no other option. So since because of its logic, what is applied for any problem, any optimization problem, it is the most important algorithm design techniques. And then branch and boundary also. Okay, but this is the top. So the last example we are going to consider for dynamic programming technique is traveling salesman problem. Already you might have gone through the lecture in your lab classes also. Just have a quick class and as per the need, we may extend it for the next class. Yeah, we completed by today's class itself. So what is the traveling salesman problem? In general, what do we understand from the term traveling salesman? Traveling salesman means the for example, medical representative. Right? So what is their job? They will start from their pharmacy, okay, and they will be given the newly introduced tablets or medicines, and that medicines they have to take it to the clinics. Okay. So they will be assigned a target. These are the clinics you should have visited by today. Okay, so the clinics will be given. Clinics in the sense the places, the addresses of the clinics where they have to go and meet the doctor present there, and they have to promote their product. So if they are starting from some place, okay, from a place X, and they have to visit some places A, B, C, D, E, and then again they have to report back to the office. Okay, they start from the office, the work is assigned from there. Okay, so they are signing in their office and they are getting the work assigned. Then they're traveling through the clinics, and after visiting all doctors, then they report back to the office and they sign out. Okay. This is what their job is. Okay. So, what is the need here? What is the solution they need here? Since they have to visit multiple clinics in the same day, and they are starting from one place, and they have to again reach back to the same place, so they have to find a optimal tour where the total distance they are traveling should be the minimum possible. Okay, that is what the solution they need in that case. Okay. So we can represent this problem as a graph, as a collection of vertices and edges. Okay. So this is their office. They sign in and get their set of clinics to be visited. Take one clinic is here, one clinic is here. Because they are having the clinics, okay, and they are having path to reach the clinics from the starting part. If this is yes, from this place to reach the clinic A, B, C, D, they have the paths. So this path may be having some cost. Okay, this will be having a cost. This will be having a cost. The petrol needs to be traveled. The petrol needed to travel from X to the location C is some C2. Similarly, C3 here, C4 here. Each will be of varying size. Some may be same. Suppose C4 and C1 may be the same caste. And similarly, it is not that always he has to go to the clinic A, then again report back to X, then go to B and then report back. No, not needed. Once for all, once he visit all the clinics, he can report back at the end. So he may not come here. Then definitely there might be some other paths available. A to B there will be a way, and B to C there might be a way. C to D there may be a way. Similarly, between these clinics there will be paths available. Okay, and some path may be of one way. Okay, so for reaching from A to C, the cost may be some C6, but reaching C to A may be something else, C7. May not be the same. The same route may not be used, maybe a one way. But sometimes it may be the same. In that case, if suppose A to B is C8, then B to A will also be C8. It depends. Okay. So we are representing this collection of clinics and the paths between them as a graph. Okay. So in this graph, what is our need? I need to find a tour. The tour will start from the place X and it has to visit all the other places A, B, C, D once. Okay, A has to be visited once, B has to be once, C and D has to be once. So after visiting these places, again he has to report back to X. Okay. So in terms of graph, the first starting vertex, starting node should be X. Okay, and after that he can visit the A, B, C, D in any order. Okay, he can choose A, B, C, D, B, C, D, A, or D, A, C, B, something. That should be visited. And after that, again, he has to visit back to, we have to reach the node X. This is what I need. In this, what optimization we need? The distance between this. If suppose I am choosing the path as X to D, then D to B, then B to A, then to C, then to X. Then I will be having some cast, right? Suppose if the cast is C1, C2, C3, C4. Then if we add this, I'm getting a value, right? C1 plus C2 plus C3 plus C4 plus C5 will be something. Similarly, if I'm choosing another path, X to A to B, B to C, C to D, D to X, this will be giving me some cost. So, like this, I can have different variety of different combination of paths from X to X by visiting all the vertices. Joel, be on time to the class. So by visiting all vertices for reaching the same starting vertex, I may be having different combinations of paths. In that, I want to choose which is having the total distance. The cost of the path needs to be the minimum. Okay, that is what the objective of traveling salesman problem is. Okay. Given a graph, given a weighted directed graph, okay, if it is not having direction, then we can take that the cost of both direction will be the same. A to B will be the same as B to A. So the weighted graph, if it is given, we need to find the shortest tour starting from a place and reaching back to the same place. Okay. And in this example, we are fixing X as the starting point, and again we have to go back to X. It need not be the same. It can be anywhere. I can start from A and I can visit through B, C, D, X, and then again I have to reach back to A. The same path can be written that way also. Instead of starting from X, I can start from this and again I can reach to A. The cost will be the same because instead of considering this edge and having the other. Okay. So that one we have to see. So for simplicity, in the example, what we are going to consider, we are going to take one as the source vertex. So 1 to 1 we have to see by visiting all the remaining n minus 1 vertices of the graph. And then this problem, what we are having, we are starting from one vertex and we are visiting through all the other vertices, and then again we are reaching back to the vertex. If we are not considering the weight, this problem is known as Hamiltonian circuit. Hamiltonian circuit doesn't worry about the cost. It needs to check whether the given graph is having a Hamiltonian circuit. What the Hamiltonian circuit means is, if I start from one vertex, whether there is a path or cycle which will be visiting every vertex just once, except the source vertex. If we are considering a graph like this. If considering like this is not having a Hamiltonian circuit. Okay, if suppose I'm starting from this vertex, I can go to here. I'm not having any outgoing edge from here. So if any one vertex is not having an outgoing edge, definitely there won't be any Hamiltonian circuit. Okay, but it is not that if every vertex is having an outgoing edge, it doesn't mean that uh, we can have a Hamiltonian circuit. Okay, but the other way is true. Okay. So this is not having a Hamiltonian circuit, but instead I'm having some other things included. If I have so, I can come from A to this node here, and then this to here, and here to here, then this way I can reach. If I'm reading, this is B, C, D, E. I can have a path from A to B, then B to C, then C to D, then D to E. I'm having a Hamiltonian circuit which reaches back to A. So Hamiltonian circuit means, or Hamiltonian cycle means, uh, whether a graph is having a cycle which will visit every vertex once except the source vertex. Okay, so the source and end vertex will be the same for a cycle. Okay, so that is modified. That Hamiltonian circuit problem is modified by having wait for the edges. Okay, here we are specifying some cost. This will be taking some 10. This will be taking some 5. This will be taking some 15. Like that, we are having weighted graph. In that, we are finding which Hamiltonian cycle is having least cost. Okay. That is what traveling salesman problem is. Okay. So what solution we are going to give? How we are going to approach this in the point of dynamic programming? Okay. We know dynamic programming will be starting its solution by considering the problem instance of size 0. Okay. So problem instance of size 0 means if I start from the office and if I'm not now, if suppose one day I'm coming and I'm given off on that day, I know I don't need to visit any clinic, then the cost of the path will be very 0, right? I can directly reach back to home. There's no need to visiting any vertex. So in that case, the cost will be 0. So from that base we will start. Okay. So that is given here as G of I comma null will be CI1. Sorry, it is not this one. If suppose that is the case, then I will not be visiting any clinic, and that will be the cost of 0. Okay. And how we are going to apply here that dynamic programming solution is, if I'm not having any intermediate vertex, okay, by not having any intermediate vertex, actually here we are going to take the objective as I need to start from the vertex 1 and I have to visit through the other vertices and again I have to reach back to 1. So from the top, if I see from the top, my objective is I need to start from the vertex 1 and I have to visit through all the other vertices and again I have to reach back to 1. Right? This is what my objective is. Starting vertex, again reaching back starting vertex by visiting the remaining vertices. Okay. So how I am going to approach this is, I will be taking within this b minus 1 vertices. What can be the optimal cost? That has to be found out. Okay. And after 1, what next vertex I can take in my path? Okay. So in this graph, if you take b minus 1 will be representing 2, 3 and 4. So among 2, 3 and 4, which vertex I am going to choose as the next vertex. After 1, am I going to choose 2, or am I going to choose 3, or am I going to choose 4? Which one am I going to choose? Okay, that has to be decided. So if I choose 2, will the cost be less? If I choose 3, will the cost be less? If I choose 4, will the cost be less? So that combinations I have to make. Okay. So if I choose immediately 2, then going through 3 and 4, what will be the cost? That I have to check. Right? So after this, again I have to reach back to 1. After visiting this 3 and 4, I have to go back to 1. Similarly, if I start from 3, I have to go through 2 and 4 some way, and again I have to reach back to 1. Okay. Similarly, if I start from 4, I have to go through 2 and 3, then I have to reach back to 1. So among this, which is giving the least cost, that result should be already available. So with that help, I will be choosing which vertex I can choose immediately after 1. So that is what the original objective, the top-down approach if we take, the final objective we are having is we need to find out the least cost for the tool from 1 through the remaining vertices and again reaching back to 1. Okay. So how we can take it? That will be g of, so this I am meaning this g of 1 comma is meaning that the cost of the tool from 1 by visiting through the remaining vertices and reaching back to 1. For finding that, among these vertices, among b minus 1, I can choose any vertex which is having the least cost. Okay, so minimum of 2 to n. So for that k, if I'm starting from k, visiting through the remaining vertices. Okay, already 1 is my source. Now I'm choosing from k. So apart from 1 and k, for the remaining vertices, what is the shortest distance? That is referred by this formula. G of k comma b minus 1 comma k. Are you getting it? This g of 1 comma b minus 1 is representing the least cost of the two starting from 1, visiting through the remaining vertices and reaching back to 1. That will be after 1, which of the vertices can be chosen immediately? I am having the option from 2 to n. So among 2 to n, which will be giving me the least cost minimum? Okay. So if I choose k, if I am choosing k can be 2, 3, 4, etc. From that k, by visiting through the remaining vertices. Remaining, already we are having 1, we started from 1. And now we have taken k, so the remaining. So b minus 1 comma k. That cost, then to reach from 1 to k, I will be having a cost, right? This is directly taking the cost from k through all these vertices to 1. So I need to add this with the cost of reaching that k. So 1k, 1 to k. It may be 1 to 2, 1 to 3, 1 to 4, anything. Plus from 2, what is the cost through other vertices to reach to 1. Okay. So this is again having the destination as 1. This is having the destination as 1. Through b minus 1 comma k, to reach 1 from k, what is the least cost? With that, I need to add the cost of 1 to k. That is what the meaning of the formula is. Okay. So to calculate this, I need, it is a recursion, right? Recursive formula. So how to calculate this cost? Okay. For that, we are given with this formula, g of I comma s. Okay. For any value I, so here this I will be taking the value, I will not be 1. Okay. When we are considering the source vertex, only this formula will be applied. To calculate that, to compute this, I need to find out g of 2, comma, g of 3, comma, g of 4, comma for other vertices. So for computing that, this formula will be used. So for this formula, I will not be equal to 1. So for the remaining vertices, not for the source vertex. For source vertex, we will be applying only this one. For the remaining vertices, Again, now what will be having? I will be having a source vertex K, so a source vertex I. Then I am having set of vertices B minus 1 comma K, right? So I will be having some set of vertices. For that, the least cost will be, again, from I through S. Among S, I can choose any of the vertices as the immediate vertex, right? So that J can take the values from S. For every vertex in the set S, I have to choose one by one. Okay. And with that cost from I to J, the cost plus. Now I have chosen J, right? So from J, comma, from J through the remaining vertices. So we are having S minus J. So what is this cost? So by adding up this, which is giving the least cost, that J will be chosen. And that cost will be assigned for G of I comma S. And for calculating this, if I'm going through this recursion, for G of I comma S, I have to calculate J comma S minus J. Then for that again, it will be getting into a recursion. So finally, when the set is becoming null, what does it mean is, from the vertex I, what is the cost of reaching directly to 1 without having any intermediate vertex? What does this G of I comma S is representing? From I through S to reach to 1, what is the cost? From I through this vertices S, again to reach back to 1, what is the cost? So if the S is empty means S is becoming null, there is no intermediate vertex. Then from I, cost of reaching the source vertex will be the cost of the edge from I to 1. So this is the base. So to solve this, this is the smaller problem size. Okay, I have told by mistake that without having any intermediate vertex, that is from starting source vertex itself I have taken. Okay, it's not that you have to take from the clinic. Okay, from the clinic, what is the cost of reaching the source without having any intermediate? Directly from 2 to reach 1, what is the cost? It is 5. Directly from 4, what is the cost of reaching 1? It is 8. From 3, it is 6, without having any intermediate. Then by having intermediate, from 2 by having 4, what is the cost? From 2 by having 3, what is the cost? From 4 by having 2, by having 3. That we have to find by having one intermediate, then by having two intermediate, then by having 3. So till we consider n minus 2 intermediate vertices, we have to compute this G minus S. So to solve this problem, we have to start from this calculation, this base G of I comma null. Again, for this also, I will not be equal to the source vertex 1. For this also, I will not be equal to 1, and for this also, I will not be equal to 1. 1 to 1, the cost is 0 only. So G of I comma null will be the direct distance, direct edge cost from I to 1, that will be taken. So this will be computed first. Then we will be considering for every I other than 1, for every I, by having one intermediate vertex, what is the cost? Okay. Then we will be having 2 intermediate vertices. Then we will be having 3. So till we are having n minus 2 intermediate vertices, this G of I comma S has to be computed for all I values other than 1 vertex. Okay. Once it is completed, then we will compute the final calculation. This is how we are solving the traveling salesperson problem. Hope you understood the formula. Now let's apply this for an instance. Okay. So consider this graph. Okay. Graph, we are having the nodes and the directed edge with the cost is given to us. And now we are representing this as a matrix. Okay. So the diagonal will be 0. There's no self loop. So its cost is 0. And 1 to 2 cost is 10. So 1 comma 2, that cell is having 10. Then 1 to 4 is 20. So 1 to 4 we are having 20. 1 to 3 we are having 15. So we are representing this matrix in the adjacency matrix representation. So we have to slowly construct our solution from a smaller problem size. So initially our problem size is none. Okay, with having no intermediate vertex, we are going to start the solution. So the base formula has to be applied. That is g of I comma null is equal to the direct distance from I to 1. Starting from I directly to go to 1 without having any intermediate. This is representing the intermediate vertex. So that has to be calculated. For this, I should not be 1. So what values we have to calculate? G of I. So I will be taking, if I should not be equal to 1, then I will be equal to the remaining vertices we are having is 2, 3, and 4. So G of 2 comma null, G of 3 comma null, then G of 4 comma null. We have to find. Okay. So G of 2 comma null will be C 2 1. C of G null will be 3 1. 4. What is 2 1? 2 1 is 5. What is 3 1? 6. 4 1 8. So smaller problem size is completed. Okay, without having any intermediate directly to reach the source from other vertices. So the direct edge cost. Okay. Then we have to increase the problem size. Okay. That is, we have to increase the size of the intermediate vertex to 1. Initially, the size of the intermediate is 0. Now we have to make it as 1. Again, now the formula we have to use is g of I comma s is equal to min. J will be taking the values from s and the cost I to j plus g of j comma s minus j. So the direct distance of I to j plus from j through s minus j. From I through s we are finding. So for that from j through s minus j we have to compute. Okay. So now we are making this intermediate vertex sizes. Vertex size is 1. So for again here I should not be equal to 1, which means I will be equal to 2, 3, 4. So g of 2. So now the size of the set should be 1. So if I have to consider, then 3 alone can be considered or 4 alone can be considered. If I consider 3 alone as the intermediate vertex, then it will be min of. So what is j? J will be yes. So j will be what? 3. So only one option is there. So there is no need of selecting the minimum. Only one option that has to be the minimum. And it will be C I J. So 2, 3. J is 3 plus G of J is 3. So 3 comma S minus J. From the set 3, if I remove 3, remaining will be null. What it will be? C23. C23 cost is 9 plus G of 3 comma null. This answer is available in the previous step. It is already memorized by the dynamic programming technique. So that 6 has to be used. So we are getting 15 as the answer. So G of 2 comma 3 is 15. Similarly, we have to find for 2 comma 4. Then we have to find from 3. Then we have to find from 4. If I consider 3, then the intermediate vertex can be 2. And similarly, the intermediate vertex can be 4. And when we are considering 4, the intermediate can be 2 or the intermediate can be. These values should be computed. And we have this result. So G2, 3 is 5, 15 and 4 is 18. Like this we have completed. So since there is no option for choosing the minimum, we are directly having only one value. Fine. Next, we are increasing the size of S by 2. Okay. Again, I should not be equal to 1. So I can be 2, 3 and 4. When I is 2, the other two vertices, the set size is 2, right? So the other two vertices, 3, 4 will be taken. If I is 3 means the remaining 2, 4 will be taken. Then if I is 4 means remaining 2, 3 will be taken. Okay. With that, we are going to take. Take that in its place. So to compute this, we have to follow this formula given here. Okay. So we have to apply min. J will be taking the value from 3, 4. J is now having two options. J can be either 3 or 4. So I can take, first let me take the value of J as 3. Okay, J equal to 3. So if J equal to 3 means then the formula will be C I J, right? So C I is 2, J is 3 plus G of 3, J comma S minus 3. S is actually 3, 4. This is my S. So S minus 3 means it will be 4. So it will be having 4. This is one option. And if J is equal to 4, then we will be having C24 plus G of 4, comma, now S minus 4. S minus 4 will be 3. So what is C23? C23 is 9 plus G34. G34 result is already available, 20. And here C24. C24 is 10 plus G4, 3. G4, 3 is 15. So I'm getting 29 and 25. Which is less? 25 is less. For which J is equal to 4. So maintain both values. Okay. We are not in need of just the cost of the tool, but also the path of the tool. Okay. So we have to maintain the cost as well as the vertex which is giving the least cost. Okay. From 2, if I immediately choose 4 as the next vertex, then the cost of the tool will be less. That is what it means. Okay. So cost is 25 and J value is 4. Similarly, find the value for 3, 24 and 4, 23. Okay. Fine. Then, so what is the size of the number of vertices we are having? 4. So starting from the size of vertex, size of the set 0 to n minus 2, I have to calculate g of I comma s. Okay. So what is my n minus 2 here? It is 4 minus 2, it is 2. So 0 to 2 we have to calculate and it is done. Okay. So now we have to apply the formula for the original objective. G of 1 comma v minus 1. So G of 1 comma 2, 3, 4. And what is the formula we had? It will be minimum of, okay. And for K we will be applying, from I 2 to n. Okay. And the minimum of C of 1K plus G of K comma V minus 1 comma K. This is what the formula is. Okay, so let us apply this. So K will be taking the values 2, 3, 4. Here n is 4, right? So if k equal to 2, then the formula will be C 1, 2 plus G of k comma, that is 2 comma b minus 1 comma 2. So from this set, if I remove 2 also, then we will be getting 3 comma 4. This is one combination. And for the next combination, let us consider k equal to 3. So for that, we will be having C13 plus G of 3 comma the remaining vertices. So it will be 2 comma 4. And the next option will be, if I consider k as 4, if I consider k as 4, then it will be C14 plus G of 4 comma 2 comma 3. So among this, which is having the least cost, that has to be applied. So C12, we are having the cost is 10. 10 plus G of 234 is 25. Then we are having C13. C13 is 15. 15 plus 3 comma 24 is 25. Then C14 we are having is 20 plus G423 is 23. And we are getting 35, and here 40, and here 43, which is least. 35 is the least value, for which k is equal to 2. So this has to be recorded. So we have found the cost, least cost. So from starting from 1, by going through the remaining vertices, again reaching back to 1. For this traveling salesman problem, we are getting the total least cost is 35. Now, how to get this value 35? What is the path of the tour? So for deciding that, we have to backtrack the value of this k and j we recorded. So for this particular solution, for the last solution 1 comma 2 3 4, we are having the k value as 2, which means from 1 I have to choose 2 as my immediate next vertex. First I have to choose 1 to 2 edge, so that I can get the least cost of 35. Okay. What are the remaining vertices I have to travel yet? I have to go through 3 and 4. So from 2, from 1, I have to immediately choose 2. And then from 2, the remaining vertices I have to travel is 3 and 4. So from 2, 3 and 4 I have to check. So from 2, 3 and 4 it is already available here, for which the cost is 25. For which we have got the cost is 25 here. When j value is 4, for this when j value is 4, we got the cost is 25. So from 2, the next immediate vertex I have to choose is 4. Obviously, the remaining one vertex is 3. So next I have to go to 3, and finally I have to go to 1. And this distance will be having this distance from 1 to 2, 2 to 4, 4 to 3, and 3 to 1 will be having the cost as 35. And this is the solution for the TSP. Any doubt?